Hello, in this video I'm going to say a little bit about specific heat capacity. This is another one of our macroscopic ways of describing things in thermodynamics, something that we have to do a lot of calculations with. And specific heat capacity is how we describe how much energy is required to raise 1 kilogram of a substance by 1 Kelvin. So it's got these units of joules per kilogram per Kelvin. And this varies from substance to substance for reasons that are quite complicated. I mean, I'll say a little bit about it, but not a lot. And it's, it varies from substance to substance. It also varies by state of matter. So, for example, in water, if you've got liquid water, then the specific heat capacity of that is, well, it's just under 4,200 joules per kilogram per Kelvin. So this is the amount of energy that you have to put into 1 kilogram of liquid water in order to raise the temperature by 1 Kelvin. If it's ice, then it's much less than that. It's only 2093. That's if the ice is about minus 1 degree C. For iron, it's way less. I mean, solid iron, you're looking at 450, give or take, joules per kilogram per Kelvin. So there's big differences here, both from substance to substance and also in the state of matter for a particular substance. And there's a lot of different factors that will determine the specific heat capacity. And it's particularly complicated when you get onto liquids because you've got a lot more movement going on in a liquid. And different degrees of freedom, because that's one of the things that affects specific heat capacity. The degrees of freedom is in the ways that atoms and molecules can move inside a substance. So the more degrees of freedom that they've got, that's going to affect the specific heat capacity. The more atoms, the number of atoms in an amount of substance. So if this is dealing with per kilogram. So a kilogram of some substances will have more atoms than for other substances. It's got a different, it depends on the molar mass, doesn't it? So the number of atoms, the degrees of freedom, things like that, whether you've got molecules in there where you're going to have different potential energies and stresses inside those molecules, all of these things are going to feed into the specific heat capacity. We know that the temperature change here is going to, temperature is a measure of average kinetic energy, because not everything's just going directly into kinetic energy when you're heating something up. So all those different places that the energy can go into, all those different degrees of freedom, the way that the atoms and molecules can move, that is all going to affect the specific heat capacity. We're not going to say anything more about that because it's just far too complicated. We're just going to be treating specific heat capacity as a macroscopic property that we can try and work it out for a particular substance, and that we can use it in calculations based on predetermined specific heat capacities. You've actually got a similar thing going on with latent heat as well. It's a very similar thing, and we'll be able to work out latent heat of fusion and vaporization in a similar way. The specific heat capacity is looking at our kinetic energy changes, our latent heat is looking at our potential energy changes. But it's the same thing. I mean, latent heat is varying from substance to substance, and you'll get a different latent heat of fusion to your latent heat of vaporization for a particular substance. So there's a load of crossover here in the two ideas. Now, if you're going to try and determine what these things are, which is mainly what we're interested in here, how to determine them and then how to use them, it's there's a couple of methods really. You'll have the one that you'll quite often do in the lab at school or college. You might want to work out the specific heat capacity of a particular liquid, where it might be water. So you get a beaker full of water, you stick your thermometer in it so you can measure the temperature at the start and the finish. You'll put in some kind of electric heater that can go off to your power supply. You're going to want to put a voltmeter in parallel and an ammeter in series, because then if you've got the time, the voltage the current, then that is going to give you the energy, because you've got volts times amps, that's your power, that's giving you your watts. You multiply your watts by the time and you get the energy. So VIT, that is equal to your energy. If you've got the energy, then you can say, okay, we've now got the amount of energy that's been put in. Particularly if you've got 1 kilogram of water as well, that certainly helps. So that's dealt with the joules, it's dealt with the kilograms. Then we look at the temperature change, and then we can work out what the specific heat capacity is going to be, because we're going to say, right, we've got a certain amount of energy that is going to be equal to our mass multiplied by our specific heat capacity multiplied by the change in temperature. Sometimes people write the change in temperature as a delta theta. Doesn't really matter whether you've got a theta for T in Greek or T for T in English. So we've got, this is our formula here, just based on our definition of specific heat capacity. So if we rearrange this, we say our specific heat capacity is our energy, that's our joules, per kilogram, per mass, per unit mass, per temperature change. So this is what we can then work out. And you can see the units here is our joules per kilogram per Kelvin. We can just plug all of this in and then work out what the specific heat capacity is. We've worked out what our energy is. We can divide it by the mass. It may or may not be 1 kilogram. We can divide it by our temperature change, and then we've got what the specific heat capacity is. Now, of course, we've got things that we can improve in this. We're getting energy loss here. We're heating up the water, and the water's radiating the energy to the surroundings. We're also heating up the beaker. You might want to insulate all of this just to make it a bit more efficient. You're going to want to stir it so you're getting a more consistent temperature inside the water. So we've got these various ways that we can improve the process, but that is one way of working out what a specific heat capacity would be. We could even do the same with a solid. If you've got a solid with some holes in it, and you can then put the electric heater inside the holes, you can still do the same thing. So we've got those methods there. Another method that you can use is the method of mixtures, and that would be where you take something that you already know the specific heat capacity for, heat it up, and then mix it with something else. So say we knew with the metal, say we've got some metal that we know the specific heat capacity for, or maybe we've worked it out for the water. We know one or the other. You heat the metal up. So let's say we've got 1 kilogram of metal at 100 degrees C, and you put that into 1 kilogram of water at 20 degrees C. And say we already knew that our specific heat capacity of water was, well, let's just round it to 4200 joules per kilogram per Kelvin. So say we knew all of this, and then you mix them together. You put the metal into the water and you say, oh, well, we get the final temperature. So say the final temperature was 26 degrees C. You can then work out from method of mixtures, from conservation of energy. So you can say that the MC delta T has got to be the same for each one of them. We're transferring energy from the hot metal to the cooler water, but that energy transfer has got to be the same. So we've got 1 kilogram of each thing, so we can ignore the M's because they're just going to be 1, and then we can say, well, the temperature change for the water is 6 degrees Kelvin. For the metal, it's dropped by, what's that, 74. So we can say, well, the specific heat capacity of the metal is going to be 4200 for the water, multiplied by the temperature change for the water, which is 6, and then divide it by the temperature change for the metal, which is 74. That's going to then give us our new specific heat capacity calculation. That's our specific heat capacity of the metal. If we still have masses involved, you'd have the mass of the water and then the mass of the metal, but we just made those 1 in order to make it simpler. So that's what's going on with method of mixtures, which is another useful way of working out specific heat capacity. For working out latent heat, we can actually use exactly the same setup as we've done here for the calculating the specific heat capacity off of the electrical circuit. We can do the same thing. We can take the liquid water, we can heat it up, boil it, turn it into water vapor, and then see how much energy we were putting in during that latent process where we're actually getting the change in state from liquid to gas. So those practicals are useful practicals. They're ones where you can actually get pretty good results, and they come up a lot in exam questions, and theoretically it's relatively straightforward to understand. We're going to do a lot of other calculations as well of what if we've got a certain amount of energy that we're pumping into a substance. We're using this E equals mc delta T equation quite a lot. What is it that we're trying to work out? Usually it's going to be, well, we know what the mass is, we know what the specific heat capacity is. We're either saying if we put in a certain amount of energy, what temperature change will we get? Or if we have a particular temperature change or want a particular temperature change, what energy is going to be required? So it's a relatively simple formula that we can just use over and over again in order to do these calculations. How much energy has been put in, or what temperature change are we going to get? These are two useful things in the real world. So we need to know things like if we want to boil some water, how much energy do we need? We can calculate that pretty straightforwardly off of this, just by we can measure the mass easily enough. We know the specific heat capacity. We can measure the starting temperature, so we know what temperature change we need in order to reach boiling point. So that quickly tells us how much energy we need to put in. Simple stuff, but effective and useful, and all at the macroscopic level. So I don't think I've really got much else to say about specific heat capacity. It's usually something that people are quite comfortable with because it's got simple calculations and it's relatively easy to understand. But having said that, we still need to talk about it. We can't just ignore it because it's easy. So there you go. That's specific heat capacity.